Hi, I'm Shalia Lopez, and this is my Constant Velocity Lab for Physics 2211 with Dr. Yonker. We'll go through the introduction, purpose, analysis, computational model, observed versus predicted graph, and finally with the what if, what does it mean, which is basically the conclusions of the entire experiment. The purpose of this experiment is to monitor the movement of an object traveling at a steady pace in a straight line. This means with no variation in direction or speed, so constant. And also evaluate the motion of an object being pushed across a table. This is the practical experiment, against a simulation developed using GlowScript. We will assume that there is no air resistance, no friction. We will be observing the displacement along the x-axis, and we will assume that the net force is equal to 0 newtons. For this experiment, we need to know about Newton's first law, which asserts that an object will keep its state of rest or uniform straight line motion unless an external force is acted upon it. We also need to know about Newton's second law, which states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, which is expressed by F equals ma, where F is the force, m is the mass, and a is the acceleration. So the force is equal to mass times acceleration. As well as we need to know the position update formula and the velocity update formula. This experiment will consist in rolling a tape and observing what happens. So in this case, the system is the tape and the surroundings are gravity, friction, and the applied forces. And we will use GlowScript for the computational trial and model. And this is the tracker model of the experiment. And as we can see, as it is moving to the right, there is an upward slope in the relationship between time and position, and this is because I chose to do it in the positive x direction, which is why we see the slope upward, like an upward slope. From tracker analysis, we obtained that our tape roll diameter is 0.085 meters, that it took 1/60 seconds per frame. We have that our initial position was 0 meters, so 0 in every direction. And to obtain the initial average velocity, we use the formula final velocity minus initial velocity divided by time, which gave us 0.52500 meters per second. For this part, we used GlowScript, and here we can see the initial conditions, where we just plugged in the values previously found, as well as the circulation loop, and we inserted the values in the code. After having the code done, we run the program and we obtain these graphs where we can see the position versus time graph as well as the velocity versus time. Now we're going to compare the tracker versus computational models and the information obtained. And the blue one is the tracker and the red one is the computational one. So we can see that they both start pretty similar, but over time, the computational one maintains its straight line. It's more linearly directed, and the tracker one isn't, and this is because the computational one assumes that the net force is 0 as it is constant. But in the tracker, which is the experiment that we did, the reality is that the net force wasn't 0 because there are more forces applied to the system, which prevents it from being completely constant. Now, for our discussion follow-up, we question what would happen if we were to flip the axis. And if this was the case, then the graph would be downward slope, as the ball would be moving towards the left direction in the x-axis, which would ultimately change the sign of the velocity, as the position would be going in the negative direction, and it would become more negative as time passes. But overall, the results would not change, as the magnitude of the position will always remain the same. So what does this mean? It means that we can't know for sure how many pushes or pulls are needed in order to have a 0 net force. And this is because of the external forces such as gravity, normal force, and the friction. And in terms of constant velocity, we know that we can't achieve it because of the acceleration that is present in this experiment.